Hello everyone, and thank you for joining me for my presentation here. According to the information you've probably received from Dr. Wiley, it's entitled ROAMGAP, Study into Non-Standard Machine Learning, and I will elaborate on that in a second here. So my project was based around building a system that's capable of doing machine learning type tasks and making progress in finding solutions to problems that we may encounter from time to time. ROAMGAP is the title of the system which I made, which I'll explain in a second. It was based around making around concepts of mutable formulas or mathematical expressions that can be changed and mutated over time to find better solutions. I'll go over that in a second in more detail as well. Meta-heuristics, which I'll elaborate further on also. And then once I had made this machine learning system called ROAMGAP, I tested it in a bunch of different scenarios and situations to see how well it would do, or not so well. ROAMGAP originally was an idea I had after I had tried making systems that learned to play tic-tac-toe, or alternatively another system that tried to move triangles along a surface where the farthest distance was considered better, and it randomly generated triangles and made progress on that. But from working with those, I came up with some underlying ideas for a larger system that would work in those scenarios as well as other scenarios, and be based on those principles of mutating and progressing like the triangles on the surface we're doing. Like my sources, one of my sources indicates ROAMGAP is a meta-heuristic, which, according to the source, is something that uses randomness to find optimal, or as optimal as possible, solutions to hard problems. So in other words, it uses random creation and random number generation to see if what was created from those random numbers is a better solution than one was previously known. And if it was, it uses that as a new basis for randomly generating off of that in small little ways, so that hopefully over time we can make these little steps to keep going towards a better solution, an ideal solution. So it's a meta-heuristic, which is kind of different than neural nets. These are both machine learning kind of base concepts. So it has a lot more in common with meta-heuristics, but it also has some things in common with neural nets, being that they both kind of have a weighted kind of aspect. Neural nets have weighted outputs. ROAMGAP has weighted algorithms, which are subcomponents of its formula, which I'll explain more in a second. But ROAMGAP itself is essentially in kind of a simplified expression. It starts with a random mathematical formula, think like x plus y plus 2 or whatever, as a big long expression. And then it takes that formula to try to give an answer to your question. Your question could have to deal with x and y. You're trying to figure out something about them, and it'll create a formula, and it'll mutate that formula over time, trying to find a better formula that better deals with the situation. Eventually, these mutations are supposed to lead to progress over time by replacing the mutated formula with the new improved version. So essentially, if the formula gets mutated and it's better at solving the problem than the old formula, it replaces the old formula, and the new formula becomes the new basis for mutation. So say we start here with the old formula, how good it is. The new formula is just a little bit better. Well, before, like the old formula, we were testing this stuff and it's all kind of bad. Then there's one that's better. Well, now we're starting here and we're testing stuff, and maybe there's one that'll be better. And slowly we just keep working our way up to better and better solutions. So ROAMGAP, the name itself, the name kind of was a combination of an acronym and a concept. The concept was that it's designed to roam the gap of potential solutions to a problem that kind of are in between what we know and what we want to solve. So it's kind of like there's this big empty area of potential solutions that we don't know which one's the best. ROAMGAP's job is to roam that area, roam that gap between what we know and what we want to have to try to find a solution that works pretty well. The acronym itself stands for Random Objectified Algorithmic Modular Generational Answer Seeking Program. So random refers to that random number generation I was talking about before. That is the basis for improvement. Objectified because it splits the concepts of improvement and all the mutation itself, all the different objects and classes and components that work together to accomplish this. Algorithmic because it's based on mathematical algorithms and formulas. Modular because it can be inserted in different situations and scenarios, ROAMGAP itself. Generational because it uses generations of these mutated formulas in a sense to make progress. Answer seeking because it's trying to find an answer to specific questions that you have that you wanted to find a solution for. And program because it's a program. So beyond that, ROAMGAP kind of has three big parts which I'll go into detail on. The first one is the logic net. The logic net is the central part of ROAMGAP. So essentially, a logic net, when you give it a specific question phrase, it can be any sort of question phrase. You can make up, gibberish if you want. It will take a formula and match it to that phrase, and that formula will return a number from 0 to 1 or negative infinity to positive infinity. So any decimal number between those ranges, right? So for example, say you had a picture, right, and you want to say, is this a picture of a cat or not? Your question phrase would be, is this a picture of a cat? ROAMGAP would take a formula, you would pass it all those pixels as data and into ROAMGAP, send it to ROAMGAP, ask it the question. It would have a big long formula that deals with all these pixels and returns a value between 0 and 1 that would tell you whether it's a cat or not. Whereas 0 would be 0% likelihood and 1 would be 100% likelihood. So you could train it over time to get higher likelihoods if it's actually a cat or lower likelihoods if it's not, based upon those formulas. And so that would be kind of how it maps out like that. So the formulas take inputs. It'll be mutated, so say the first formula for telling you it was a cat, say it was a picture of a cat, right? And it said 0, when it really was a picture of a cat. Well, that wouldn't be very good. But then it's a mutated version that says 20, right? Well, that's a little better. 100 is ideal in percentage-wise, but that 20 will be a new basis, and we'll keep trying new versions of the formula that return values that are better and better for that situation. Of course, it'd be more complex than that in actually training, but that's kind of the base idea. And then say we also want to ask the same logic net. Is this a picture of a dog? Because we want to be good at identifying cats and dogs, for example. What the logic net does is it has, because we don't want to get those questions mixed up and it's determining if it's a cat or a dog, it would essentially take each question, is this a cat, is this a picture of a dog, and create a formula that matches with each of those and stays with those for the lifetime of the logic net, so things don't get confused or jumbled over time. So the logic net itself, here's kind of an overall diagram. At the top we kind of have the logic net, just kind of expressed as itself. The next more important part is to see the map of questions there in the middle right. The map of questions is what takes your question phrase and matches it to a mathematical formula. And then we can see at the bottom of that kind of section we have the algorithm, the formula, question node and formula, and then the formula has algorithm weights and algorithm indexes. So the formula's weights and indexes correspond to algorithms, which are shorter phrases of mathematical expressions, and the weights are actually constant values that can also be mutated to advance the logic net. Then the algorithms can be broken down to items and operations in various lengths, and the items can refer to data you pass into it, they can refer to constants and other things, and the operations can be any mathematical operation that is constructed inside ROAMGAP as I set it up. So the logic net itself, the way it kind of works with stuff is you pass it in the question, goes to the logic net looks at the list of questions that it's aware of, and then what it'll do is it'll say, okay, here's the question that you asked me, it matches this question I already know. It'll say, okay, that goes to this node because it matches the question I know before it goes to this node. So it goes to the node has a specific formula, the formula takes the data you pass into it with that question phrase, computes it, and returns you an answer from either 0 to 1 or negative infinity to positive infinity. So that's the logic net. That's how we do the calculation of relative to your question phrase. That's how we have something that's mutable and able to be mutated and changed slightly to try to find a better version. The next step is actually keeping track of which logic nets are better and which logic nets are worse, so we can advance over time. That's the duty of essentially the ROAMGAP, the kind of overall core, the structural managerial core, the interactor. The interactor is what you do when you actually want to interface with ROAMGAP and make progress learning something. You'll create an interactor. The interactor has I'm not going to get into too much in the details, but you can see it has, the top of the interactor, we have hierarchies, which kind of are sets of logic nets that complete a specific independent task. The champion up there at the top left is the best logic net so far, the one that has performed the best in solving our question, be it identifying a picture of a cat or a dog or whatever, right? And then we also have an array of cells. Each cell can be viewed as an ancestral chain of logic nets that are progressed over time and kind of are isolated. Once we get through the cells, we see which logic net from the cells is best and compare that to the champion to see if it overcomes the champion or not. The new champion then becomes a basis for filling in the cells with logic nets to be tested against in the next ancestral chain. So yeah, the interactor connects ROAMGAP to the external program. If you're interfacing with ROAMGAP, you go through the interactor. The interactor manages all the objects that control the mutation, the advancement, the testing of logic nets to see if they're doing better. But essentially, part of the mutations, and so think about our solutions we're trying to find. They kind of can be viewed as a graph where we have like a, polynomial type function where it's got a bunch of curves and hills and stuff in it, right? We're trying to find the best solution, and you can view it kind of like seeing the tops of those hills. There's a bunch of little hills, but we're trying to get the best solution possible, which is kind of the tops of those hills. The problem is, say we found one formula, one logic net, that's somewhere on that hill, right? We don't want to get caught on that same hill because there could be another hill that's really higher, but at the same time, we want to keep getting higher on this hill too. So trying to prevent being stuck on the same hill, we start with big mutations. So think about, here's the point on the curve we're kind of going around. Big mutations would just jump all over the place and test to see how it would turn out. If it turns out one of those is on a higher point on a different hill, then we just go over there. But over time, there's a less likelihood those big mutations are going to actually work out and find a higher hill. So the mutations are going to keep shrinking more and more, so they're kind of in a local area to what we've already tried, like the champion logic net, for example. So it makes an increased chance we'll reduce the mutations over time to try to at least get some advancement on this hill, if nothing else. Now, if we fail to do the big mutations get anywhere, if we fail to do the little mutations get anywhere, that means we're at the top of the hill that we can find for that ancestral chain, that cell, essentially, and then we move on to the next one. So essentially, the interactor will test all these cells that try to get to the tops of the hills, and then when they get to the tops of their own hills, these, say, 4 cells will find which one got to the highest hill, which one was the best logic net. That will become the new champion for the next round of filling the cells with pseudo-random logic nets and seeing how high they get on hills. So the third component of ROAMGAP is the external program. The external program is what actually implements ROAMGAP and uses the interactor, uses the logic nets to do a certain problem, right? So like the one that identifies, say, is it a cat in the image, right? That'd be the external program actually managing that aspect of it that's specific to the problem to be solved. So for another example might be, say, we're trying to build a bridge, engineering, right? We're trying to find a bridge that fills these positions and supports weight. The thing that actually controls the bridge parameters and building the bridge and testing that and simulate that physics-wise would be the external program. That wouldn't be ROAMGAP. ROAMGAP is only there for the learning portion of it. So to accomplish this, the external program needs to have specific question phrases for ROAMGAP to answer. So like, is this a cat in the image? Is this a dog in the image? It needs to be able to pass information, data from the environment into ROAMGAP. Sometimes there's no information, but sometimes there is. In the case of the picture of the cat or the dog or whatever, that's the pixel data that they would be passed into ROAMGAP. It needs to tell ROAMGAP how well it did, how well a specific answer solved the problem or not. Then it also needs to be able to do this over and over again in order to actually learn. If it just does it once, it's not going to really get much anywhere. It needs to keep going over and over again. Okay, so to actually test this now, I did it in a bunch of different situations and saw how ROAMGAP would perform to actually get some idea of maybe how it acts in comparison to other machine learning programs, or whether it's just decent enough in and of itself. The first situation was AI Runner. I had mentioned the triangles moving over their terrain earlier. This is the actual scenario that does that. So ROAMGAP's trying to build a series of triangles and joints connecting them, and motors that control the joints, that builds this mass organism of sorts that is capable of moving across terrain as far as possible. So in a 2D space, it's just moving to the right as far as it can. This way, actually, from your perspective. So, for example, for asking questions to ROAMGAP, like the cat picture or whatever, it would start by asking, how many triangles should there be? That'd be the first question. It would return a value between 0 and 1, say. We multiply that by the maximum number of triangles we want, say 20, and then we get our number of triangles, and then it would iterate through all those numbers of triangles and say, for example, what is x-coordinate 2 for triangle 6, or what is x-coordinate 3 for triangle 6, what is x-coordinate 7 for triangle 7, and so on and so forth, until we get all the data we need to know about where the triangles are, how many triangles there are, where are the joints, how many joints, etc., etc. Then the external program takes that information and actually builds the triangles and runs the simulation, and will even ask the ROAMGAP about every frame of the simulation, should this joint be moved, or what joint should be moved, or so on and so forth. So ROAMGAP actually has some active logic going on while it's simulating. Then ROAMGAP will be told by the external program how well it did based on how far that triangle mass went. So now I have some examples to show of how this progressed. So the first one we have here, we have 2 over here on the far left which have like kind of a bumpy terrain. We can see that it developed this shape that has 2 triangles where it has a foot kind of bouncing along, and this long head thing that kind of prevents it from getting caught in the ridges. Below it we have a sort of pedestal object that kind of jumps, as we can see there. It jumps and just bounces a little bit and then drops and just stays there for the rest of the time, which gets it far, but it doesn't just keep going. But it seemed to do okay at least. Now these are all evaluated for a certain limited number of times. They don't let them run until they stop. They run for a certain amount of time, see how fast, in a sense, they can get far too. Now on the right we have these 2 scenarios with a flat terrain. The top one here is just kind of hopping along. It seems to be doing decently, just an interesting one. The bottom one here, and kind of going in slow motion, is similar in a sort of design, except the foot on it kind of grabs the ground and propels it forward a little more. But there's just some examples of how it learned to move on the terrain over time. Now those examples kind of have more of a passive logic. They design the triangles, and the triangles just kind of run on their own because the little feet on those triangles are actually just constantly trying to move. So they get stuck like this. When they hit the ground, they get pushed back, and then they move again. So they're not actually thinking to move. They just kind of automatically, like a spring, I think, from what I understand it. This shape, however, is using logic to know when to bounce and move around. So in the example, you can see the first video right out there. Positive motor speed is 0 for, it's telling this motor essentially to move and go down, so it falls, right? And then we can see it's, this data down here is telling us, let's say, then it's down, it's saying negative motor speed 0, reversing itself, I think, and then use motor joint 0, tells itself to jump back up. So it's actually giving responses to tell itself to move rather than using a spring-like motion where it would take advantage of the physics. And then, so you might have, if you had seen my earlier presentation before I started working on ROAMGAP, there was a more primitive version of it that created shapes more like this, that were look more complex. So I was curious to think about what that meant. But I think in the end, the new ROAMGAP, which is producing shapes more like this on average, is actually more streamlined. The old version, you can see it's not really moving as far, even though it looks more complex and more is going on. The one on the right is actually more kind of streamlined for the task and doing more simply. Even though all the shapes look more similar in the newer version, all triangles kind of just jumping and moving along, they're actually, I think, more efficient or more quickly coming to a similar, more ideal solution than the old version. Another scenario I tried to get ROAMGAP to learn from was checkers. So essentially, I would to ask ROAMGAP which move to take, I would figure out what would result in the board if it took a certain move. I'd ask it how ideal is that board configuration. It would give you a 0 to 1 or whatever evaluation saying how ideal that board configuration was, and the one with the most ideal configuration after the move that caused that configuration was chosen as the move it would take. So essentially, I would make ROAMGAP compete against itself by having two logic nets kind of take responses, and I would pass results back into both at once, whether they won or lost. Here's kind of a video of how I'd be learning. You can see it would show some game results as it went along. However, when ROAMGAP, when I would actually play it, I noticed what it would end up doing, it was when it would play itself, it would just try to block the king kind of positions on the board so that when the other opponent tried to get down there, it would get stopped. And I had a rule saying if you can't move, then you automatically lose. So when I would play it, essentially what it would do is it'd break a king, get one piece kinged, and just move it back and forth and hope that I would get blocked in the end, which it wouldn't really happen. I don't know if it ever happened, really. So I would usually beat it okay, so it wasn't the best at learning checkers based on the way it was set up. Another situation I tried was formula recreation. So I would start with a random kind of, not a random, a mathematical formula I had set up within the external program. ROAMGAP's goal was to try to make an approximately similar formula that would output the same results. It wouldn't have to be mathematically, conceptually the same, but it had to give about the same results. So closeness of how the outputs work. So I would give it 2,000 randomized values, 1,000 between the range of 0 to 1, and 1,000 between the range of 0 to 10, and then the 1,000 range of 0 through the 1,000. In the last test, anyway, and ROAMGAP would be evaluated for how close it would be passed in those values, and it would be evaluated for how close those values were to the values given for the mathematical formula. And the goal would be get values that were outputted as close to the mathematical formula. So here's some charts showing. So here's this example function: sine of x plus 6 over x plus 4 to the x over 8 to the 1.2 power. To 25 generations, so I let it run for 25 generations. It had about 98.58% accuracy and recreating a similar formula. So we can see the red circles here. That is the actual mathematical formula. The blue circles, which are kind of sort of on the mark, are its guesses at recreating the formula approximately. So we see it was trained within 0 and 1,000 values, and it was kind of close, but surprisingly, in a range from 15,000 to 1510 of the input values, it was actually fairly on the mark, even for values it wasn't trained against. So it seems like it's not like overfitting, it's actually being able to dynamically respond in an accurate way. Now, granted, these are huge values. 1 plus 136 is just like 10 to the 136 values. It's really fine values, but compared to the rate of growth of the function, it still seems to be pretty accurate, even though we might not be able to see all the fine differences. Here is its recreated formula. It's a lot different looking than that sine of x, but it actually turns out to look similar. Photo recoloring. This is another example I tried to do where ROAMGAP would be, I would start with a colored photo, right? I would turn it into grayscale, make it black and white. Then I would ask ROAMGAP, go through pixels and give it some data about the pixel, about the surrounding pixels in black and white, and ask it what color should it be on the red channel, the blue channel, the green channel. Essentially, I ask it to recolor that pixel. I'd go through a bunch of pixels and see how close it was to the recolored photo, even though it was only given the black and white photo. So here's some examples here we have a color sky, black and white, and then the recolored one is interesting. It has this blue sky really close looking, but the clouds are all green for some reason. We have a colorized field, black and white, and then the recolored field almost looks like it has a filter over it, like a sepia tone or green or something like that. And the clouds have some yellow and slight red, which is interesting. So ROAMGAP doesn't seem to be perfectly accurate at this. However, I wasn't showing it the whole image to learn from. I was only using some small portions, because showing it all that pixel data for the whole image at once and asking it for a result was it just took way too long to ask that over and over again for me to make much progress in training it to learn how to do better. It's possible if I ran it for the whole image on a much faster computer, I could have better results. And then for fun, I tried taking the one that was painting that field earlier, this one down here, at the bottom right, and I had it try repainting the sky, and this is what it came up with, which is interesting, I guess, because the clouds kind of had a similar effect that they did in the other image, which makes me think that if we could have separate ROAMGAPs that are trained to do particular topics, a ROAMGAP that repaints the sky, a ROAMGAP that repaints the fields, or a ROAMGAP that repaints people wearing these images, you could take the same black and white image and have the different ROAMGAPs that are specialized in different components of images pass over it and color those sections of it, and in the end you might have a more accurate image. Awesome. CAPTCHA analysis. So CAPTCHAs are things which are text to try to detect if a person or a bot is using a website. It's essentially text that's kind of skewed and altered in ways. So I tried taking images of text that was skewed and altered, passing it into ROAMGAP, and waiting for it to tell me what the text was. That wasn't happening very well at all, because it's just too difficult having all those letters at once, all that pixel data, and to deal with figuring out what the letters were, where they were in the image, and with all the alterations and skewing of the letters and all that, just too difficult for it. So I came up with a similar situation, which was character recognition. For character recognition, I found this data set of hand-drawn digits from 0 to 9, right? I took 30 to 70 examples of these, depending on the test, passed it into ROAMGAP, and had it try to tell me what's the likelihood it's 0, what's the likelihood it's 1, what's the likelihood it's 2, etc. The digit with the highest likelihood was the one it would guess was the actual digit. So here's some examples you can see of the this database, at least for the number 0, there's thousands of these. But I tried drawing 20 characters on my own to see how it would guess what those ones were. So you can see here the first row is the image itself, the second row is the rank relative to the other numbers. So there are 10 ranks. A rank of 1 means it guessed that the correct letter, so say the first one that's a 0, it guessed that 0 was the second most likely option out of the 10 digit options. So say the last 2 9s here, it guessed 9 was the digit, and it got it right because 1 means that it was the most likely, so it would have selected that 1 out of the 10. The average rank was 3.65. At first glance, it might seem that it's like, oh, just lower 50%, so that's not too great. But this isn't asking for likelihood. That likelihoods were much better on an individual basis. This was, because it was a combination of all 10 digits at once, just kind of guessing probably would have ended you up at maybe like, I don't know, 1 out of 10, 10% accuracy? I don't know. But this seems to be a little bit higher, but it's not accurate enough to be good, I would say, at character recognition. So overall, I'd say ROAMGAP generally does better in problems that require a creative solution of sorts, or at least those that have a big, large amount of potential good solutions. But I think it has problems with those that have like specific strategies or need specific logic in order to accomplish it. Like checkers, there's only a certain amount of strategies that are actually viable to win in checkers, so it's hard to find those. And maybe character recognition too. There could be only a few ways to tell if a character is one, or a letter or number is one or the other, so it's harder to find those specific solutions. So in other words, it might do better when there's a sea of good solutions and it's looking for an ideal solution. It might be better at that because it can find solutions and progress to it. But when there's a sea of kind of mediocre or garbage solutions, it's going to be I think it just has trouble finding that one kind of more of a needle in a haystack, maybe not necessarily, but of some sorts, rather than a sea of needles that are better or worse. Yeah, so it could be that, could be the problem. It could be ROAMGAP just needs more fine-tuning to work better. I was running this on my laptop, so that might not give me enough power to actually, do it like on a supercomputer or something would, let it run for longer, let it see the whole image in photo recolor, which would probably get into its advantage more. There are some potential applications for ROAMGAP, I think. One of them might be in general purpose kind of physics simulation or learning for engineering, maybe. So say, like I talked earlier about building a bridge, so you need to build a bridge that can hold a certain amount of weight, it has constraints, it has to be connected on certain locations, and you have a certain amount of dollars worth of materials or whatever you can use. you could just let ROAMGAP run for a while and let it build bridge configurations, and it could come up with some interesting solutions that might be viable in the real world. There might be other things like that could be interesting. And if nothing else, ROAMGAP at least kind of shows some new concepts for machine learning that could help to make machine learning more accessible or maybe more modular in nature. Because the question asking model, like where it actually take literal English, not English necessarily, but linguistic phrases that you could put into it to kind of help you organize what questions you're asking. External evaluation, that could be how the external program actually evaluates the system directly rather than having some sort of internal inside the machine learning system. And I don't know if there's really another modular kind of meta-heuristic type machine learning system out there where it's able to just kind of use random numbers to improve. I don't know if there's one like this out there for sure, but that could be a potential application if anyone's needing a general purpose type meta-heuristic machine learning solution. So here's some sources from the presentation, and thank you very much. I will probably be answering your questions for the event here soon, and see you soon.